Okay, welcome to the GeoPython track. Our first speaker is Michael Turner. He is senior engineering and geologist, and he worked on many infrastructure projects and does many things about automation. So let's start with his talk, 3D ground modeling in the civil engineering industry, an open source workflow.
Does that screen come through? Yeah, yeah, so as Martin said, I'm Michael Turner. I'm going to present some early stage sort of proof of concept testing that we've done at Atkins within the ground engineering team on an open source workflow for 3D ground modeling. So first, I thought I'd give just a quick introduction as to what ground engineering is within a civil engineering context. And basically, my team is concerned with how any structure interacts with the ground. As you can see from the pictures, these structures can be very far-ranging. Within any civil engineering project, the ground is usually the largest risk factor. That's because it's a natural material, it's not manufactured to any specification, and it can be highly variable. And usually we have relatively little information on it. Because of this, there's a really well-established process of using ground models within the industry to help understand the ground and then to communicate and manage the risks associated with it. So the ground model progresses from a conceptual outline of the conditions that you might expect based on the general geological context of the site, through to an observational model that's based on investigation and test results, and then finally through to an analytical model that's actually used to do the design calculations. And over the past few years, there's been a real acceleration in the use of 3D digital ground models to better visualize the problem, especially for the observational model stage. At the moment in the industry, in the UK at least, there are several competing commercial 3D ground modeling packages. And here are examples from several of them, all currently in use at Atkins for different market sectors or for different clients. And they all have various advantages or disadvantages. One of the big disadvantages is that these don't necessarily talk to each other, and there's no well-established common data format for transferring the models. Another common theme is high license fee, and this is a problem for adoption for two reasons. Firstly, it's a heavy burden on small firms or independent consultants, especially if there are several different commercial packages which get used on different projects. And secondly, even a large firm like Atkins, it means there are a limited number of users because you don't want to pay for everyone to have a license. And this means that the models are a bit limited in their use, and in practice, the 3D ground modeling just doesn't get adopted for many smaller projects. So to overcome this, we decided to undertake some sort of early stage proof of concept testing for a workflow for 3D ground modeling that just uses solutions that already exists out there in the open source ecosystem. So the workflow itself is super simple. It's just ingestion of this AGS data format into a general Python data structure. We then use the Genpi project to calculate the 3D ground model, and then output and visualization in VTK. So this AGS data format in the UK onshore industry, at least, is a standard data transfer format for geotechnical data called the AGS format. And it's used pretty universally in the UK. So the format itself is quite old. As you can see, it's set up in 1991. It's been updated a couple of times since then. But basically, it's a plain text file that contains a series of different tables for handling the different types of data that typically get collected during a ground investigation. So we have a table containing the overall project information, and then tables containing the data for each individual borehole or location, and then a series of tables for all the individual test results and things like that. Now, plain text files are obviously super easy to read into Python, and we wrote a simple parser to read the plain text file and then organize the data into the structure shown on the right. So we have an overall project class, which contains all the project level information, including a list of all the individual investigation locations. And then each investigation location contains the information on its location and how it was drilled and things like that. And then also contains an ordered dictionary of each of the strata that it encountered. And then each stratum contains its material description and its classification. We set up the structure with the intention that it can be extensible, so in the future we can have the test results for each individual stratum contained, and also interpretive parameters for use in analytical models at later stages. But at this point, we're only interested in the location, positions, and the strata classifications. There's a couple of things to note at this point. The first being that the AGS data that's received from the contractor who's actually on site drilling the boreholes and things is notoriously bad for containing lots and lots of errors. So any complete workflow would need to include extensive error checking to ingest the original data. And the second point is that there's typically an initial review and interpretation stage carried out by the consultant to either apply or to update the strata classifications and make sure the classifications are applied consistently across the whole project. And all the data that we've used in this initial testing so far had already been through these initial error checking and interpretation stages. So next, after we'd ingested the data, we used Genpi to generate the ground model. These are a couple of the standard examples published in the paper shown, which was published setting out the version 1 methodology for Genpi. The work that I've done here was with version 2, and I think they're already up to version 2.2. So it's being really actively developed as a project. And the way Genpi calculates the 3D ground model is quite interesting. Most of the commercial packages that I mentioned earlier, if they do any automatic modeling at all, they just do sort of simple linear interpolations between the different locations, or maybe simple splines. Otherwise, they tend to rely on the user to do a lot of manual interpretation, so maybe in a series of cross sections, which the system then uses to build the 3D ground model. Genpi, on the other hand, uses the potential field method, which is described fully in the documentation and in the paper shown. I'm not going to go into detail here, but very briefly, it kind of mimics the way a geologist is trained to think about the ground as sequences of strata separated by unconformities and faults. And then from this, Genpi is able to automatically generate the 3D ground structure from the input observation points and sequence information. Now, this technique was developed for modeling quite large-scale features in sort of hard rock proper geology, if you like. And that's quite different from what we're normally worried about for civil engineering projects, which are often dominated by near-surface, highly variable deposits. And this could cause some challenges. For example, it's not immediately clear that the interpolation function used to calculate the scalar field would necessarily be applicable to the superficial materials, but we thought it'd be interesting to give it a go and see. So this is the first of our test models. It's output in VTK and viewed in ParaView here. Now the first thing that you notice is that it's a cuboid, which might make sense if you're modeling a volume of ground below the surface, but it doesn't make much sense for a typical engineering problem at the ground surface. But because the voxel data is in real world 3D coordinates, we can very simply crop the block based on raster data, for example, LiDAR data that we have for the site. So if we do that, we can start to see a bit more of what we're expecting. So here we've got a road coming through on an embankment, a bit of a road junction and another one crossing underneath. Now, once we've got this, the first thing that the engineer wants to see is the raw data. And because we've got each of the locations saved in our Python data structure, it's really easy to build each one as its own little borehole stick in VTK and then add them into the model. So now that we have the borehole sticks as well, we can start to evaluate how well we think the models predicted the ground conditions. If we look first at the grayish color on top, that's made ground. We expect made ground to be pretty difficult to predict. Because it's put there by humans, it's really irregular and it's very discontinuous. And we can see in this model that it's kind of broadly associated with the roads and the embankment in the right place that you'd expect, but the extent is probably a little bit over predicted. If we turn off the made ground and just look at the natural materials underneath, then what can we see? If we look first at the deeper layers, these strata are more continuous across the site. And we can see that we appear to be getting quite reasonable changes in thickness and changes in level that pretty well reflect what's going on in the data. And looking at the shallow materials, they also seem to pretty well reflect the data. It seems to struggle a little bit in this region with the yellow river terrace deposits. And that's possibly due to the vertical resolution of the voxels. So the river terrace deposits here are very thin, and each voxel is comparatively quite thick, so it doesn't seem to be getting picked up too well. Another thing to notice is in this top right-hand corner, there's no data, so the model's really uncertain there. And that's a really common issue in civil engineering projects. If we move on to a second example, you can see it even more clearly. So this is a railway scheme. There's a railway embankment running through the middle here. There's actually a junction and another embankment coming down here and one down here. And the scheme we were working on was worried about this embankment curving through the middle. So what you end up with is all the investigation positions lined up along that embankment, and then no information on either side. And that's nearly always the case in any linear infrastructure scheme. What we can do is quite simply calculate a buffered area around those locations and then really easily crop the BTK model to that area. And now it looks much better. And this simple step is actually something that several of the commercial packages really struggle to do at the moment, but it's really simple to do in Python and VTK. So if we look at this model, we see similar things to before. The deeper, more continuous strata seem to be pretty well captured. The more discontinuous strata at the surface, a bit less so. In this example, it's actually not managed to make the material in red, the track bed material, quite continuous enough along the embankment. Now, given the complexity of the near surface materials in particular, and typically the sparse amount of information that we have, what the engineer wants to do next is to go in and edit the model based on what their expectations of the ground are given the context. And this is an absolute must-have requirement for 3D ground modeling within civil engineering at the moment. It's something that this workflow doesn't yet have. Some potential directions this could possibly take is perhaps direct editing of the voxels in a block model like this, which could work quite nicely. Or alternatively, you could add additional manual control points, perhaps through some facility for the user to interpret cross sections or aerial extents of different strata. Now, obviously, if you do that, you don't want to change the raw data or to mix the raw data in with the control points. So you have to build a more complete system for handling those additional control points and tracking them separately to the main data set. So in summary, the open source workflow that we've started to explore here seems pretty promising in that it automatically and quickly generates pretty reasonable first guess 3D ground models in a civil engineering context. And the open source framework also creates some really good opportunities for extensions to the system, and it's got tremendous flexibility in how other technologies can be linked into it, much more so than the commercial packages. The VTK format also seems potentially useful as a general format for 3D ground models. It can handle both surfaces and voxel models. Voxels have an additional benefit that each individual voxel can have parameters associated with it, which could then feed directly into analytical models. VTK can also handle structured and unstructured messages, which could feed into analytical models. And all these things could help to improve the interoperability between the observational model and the analytical model, which would be a big improvement. And then obviously to get any sort of established common format for 3D ground models, we'd need some buy-in from the different commercial packages, and we'd need to consider wider industry requirements. Finally, the main blockers to wider use of an open source workflow like this within civil engineering is we need some sort of system to do the initial viewing and cleaning up of the raw AGS data. As I mentioned, we currently use a completely separate commercial package to do this. We need some sort of facility to interactively edit the model and let the engineer apply their own judgment based on the context. It's especially important for the near surface layers. And something else that the commercial packages are very good at, but this workflow is currently missing, is easy integration with other data formats that are used within civil engineering, so that you can start to view other data, so GIS data or CAD design data in relation to the ground model. And then lastly, generally, there's a very low level of coding skill within the industry. So even the very small amount of coding that was needed to do this is beyond the vast majority of users. It's obviously something that the industry itself needs to improve, and it's slowly getting better. The flip side of that is that where there are pockets of skilled people, there's the potential for them to make some really important contributions to open source projects like the ones I've shown here, and to then to really drive change in the industry that ultimately lowers the cost of building infrastructure for everyone. Thank you for listening. That was everything I had to say, and I think hopefully we've still got another couple of minutes for any questions and things.
Thank you very much, Michael, for this interesting talk. Are there any questions? You don't forget to use the Q&A button, or you can also use the chat in the GeoTrack. I don't see any question at the moment, so I start with my question. I never used VTK so far. How is it regarding a performance, for example? Is it okay, or does it need improvement?
So for what we've done so far, it's been very good. it has far more functionality than we actually need for doing what we were trying to do. It's got lots of very useful geometric operations and things. The only thing where this kind of initial phase stopped was the ability to easily edit the models, which needed a bit more sort of front-end programming experience than we had immediately available, but could definitely be done for certain.